Well, when I was working on this, I was in Garching.
I see.
Now
Perfect.
I'm based in Paris.
Perfect. Right. And you'll talk about a spectral gap implies rapid mixing for commuting Hamiltonians.
Okay, thank you for the introduction. We're going to continue looking at some physical systems now. And I'm very happy to present this joint work with Alvaro, Angela, and Cambus. So what we're looking at is quantum lattice systems. And it's a fairly common fact that lattice systems that interact with an environment, or general physical systems that interact with an environment, will thermalize under relatively in relatively generic settings. And this can be a good thing, this can be sort of a problem. And understanding this thermalization process is not just of physical interest, but also if we want to sample the Gibbs state, and with Gibbs state, I mean the thermal state of the system, or if we want to prepare the Gibbs states, then it's sort of nice to know when this thermalization process happens very quickly. And I'll, in just a few minutes, define properly what all these quantities mean. But knowing sort of when we have this rapid thermalization, or as I called it in the title, rapid mixing, is also nice if we want to know certain properties of these thermal states, of these Gibbs states, properties that are of interest if we want to do Hamiltonian learning, for example, or statistical mechanics. But this also sort of plays a role in quantum algorithm designs. And there is going to be a talk tomorrow by Chen et al. On sort of quantum algorithms to sample Gibbs states inspired by this physical thermalization process that we're going to be talking about here. And another sort of connection of rapid thermalization is with passive memory devices, namely that if we know that our system thermalizes very rapidly, then we cannot passively store quantum information in it very well. So it's nice to have a general theory of thermalization of quantum spin systems. I know which systems thermalize rapidly and when they don't. And this work is a step toward such a general theory. Before I go into sort of the results, I'm briefly going to talk about the setting. So we care about quantum lattice systems where the lattice satisfies two properties. One is that it's two colorable, i.e. we can assign each vertex a label, say 0 or 1, such that neighboring vertices don't share the same label. This is more of a technical thing from the proof. We can generalize this somewhat, but there is no physics really hidden in there. The second assumption that we require of this lattice is that it has what is called a finite growth constant. The definition of this I'll skip here because it's not the most intuitive thing, but you can sort of think about the lattice not growing too quickly, like regular lattices. And what do these lattices look like? So for example, the one-dimensional quantum spin chain or the d-dimensional hypercubic lattice or trees are examples of lattices that satisfy these two properties. And these are usually also the most commonly considered lattices in the literature. Now we do quantum physics, so we need some Hamiltonian. And we will be considering so-called geometrically local commuting Hamiltonians. You might already know what geometrically local means. It means that our Hamiltonian on our lattice gamma is given as a sum of terms that act on geometrically local regions of the lattice. The word commuting means that each of these potential terms commutes with every other. An example of this might be the toric code or the Ising model. Here again, geometrically local is a physical assumption that is somewhat necessary because for long-range interactions, we do expect different physics, whereas commuting is more a restriction due to the proof that we're using. But these class of Hamiltonians are quite commonly talked about in the literature. Now, we need to talk about which kind of thermalization, which kind of dissipation do we think about. Well, we're not thinking about local depolarizing noise. We're thinking about a very physically motivated type of thermalization, which was introduced by Davies in the 70s and 80s, which is called the Davies thermalization. And this is a family of Lindbladians. So we consider quantum Markov semigroups that describe the dynamics of our system. And these Lindbladians are made up of our commutant with the Hamiltonian and local noise terms. The fact that this thermalization noise is local comes from the fact that the Hamiltonian is commuting. The exact details of this are not that important. What's sort of important is that if we consider our spin system state at time t, and if we know that this Lindbladian is gapped, then we know that eventually it will map every initial state to the thermal state. Now you might say, okay, so we have a criterion, namely the gap, which implies thermalization, so we're done. But actually, we're not quite done, because what's important is how quickly this thermalization happens. Again, think about if we want to prepare this skip state, if this happens very quickly, then sort of inspired by nature, we might be able to implement an algorithm that mimics these Lindbladians and then produces us this state very quickly. If this doesn't happen very quickly, then we're kind of out of luck. Now, before I define what rapid thermalization means, one sort of remark. We care about thermalization in the thermodynamic limit. Hence, we always think about some infinite lattice. And then we look at the dynamics on finite connected sublattices and see how this scales with the size of this sublattice. And it turns out that this gap is a necessary condition for thermalization. Hence, if we want thermalization in the thermodynamic limit, we need that the infimum over all these gaps is lower bounded. And if this is the case, then I say, or then we say the system is gapped. So if I say gap or the system is gapped, then I always mean the infimum of the gap of our family of Lindbladians. Now, how might one describe thermalization time? One very common way to do this is via the so-called epsilon thermalization time or epsilon mixing time. This is the smallest amount of time that has to pass such that any initial state is only epsilon indistinguishable from the thermal state. This is quite a natural notion, and we use the trace distance here. And now what we care about and what this work is about is the scaling of this thermalization time in the size of our finite sublattice. Again, if the scaling is nice, then you can imagine preparing and sampling Gibbs states efficiently. If it's not nice, then we might have a problem. And we say our system is rapidly thermalizing if this mixing time scales polylogarithmically in the system size. Now, via sort of a naive inequality, if we have a gap, then this directly tells us that the mixing time is lower bounded by something that scales linearly in the system size. But from classical spin system thermalization, we know that for systems with geometrically local Hamiltonians, this is not always optimal. So we need to find a way to get a better bound on the mixing time. And one way to do this is to turn to information theory, quantum information theory, namely the so-called modified logarithmic Sobolev inequality. The details of this are not that important for this talk. Essentially, it's an inequality that gives us a constant alpha, which describes an exponential decay in the relative entropy between our spin system state at time t and the thermal state with decay rate alpha. So what I'm going to be doing in this work is giving a rather simple condition on the existence of such an alpha, because if we know that such an alpha exists and scales nicely, then we can show rapid thermalization. Essentially, if you apply Pinch-Schuh's inequality to this exponential decay, you get a mixing time bound that scales as 1 over alpha times the logarithm of the system size. So if we get an alpha that is logarithmically decreasing or constant, then we get something that's rapidly mixing. Now, let me briefly recap and put this into a diagram, what I just said. So we've seen that gap implies polytime mixing, and we've seen that MLSI, which scales suitably, implies rapid mixing. Now, for classical systems, we know that gap implies a very strong form of spatial clustering, which, if you attended the talk by Quora this morning, it's a similar condition. It's a decay of the max mutual information, which is not conditioned on sort of a third system. And then this decay gives directly the existence of a suitable constant. Quantumly, however, this is somewhat more difficult because gap only gives us, or only in parentheses, sort of decay of covariance, which is in physics circles the normal decay of correlations. And in quantum theories, there is in general a gap between decay of covariance and decay of mutual information. So decay of mutual information always implies decay of covariance, but the other way around in general does not hold. However, here is our first main result, and that is that for geometrically k-local commuting Hamiltonians, Gibbs states that satisfy decay of covariance, meaning exponential decay of covariance, also satisfy exponential decay of mutual information. In fact, this is sort of a more formal statement. If we have that the marginals of the Gibbs state on some region A and C, which are distance L apart, if the state is approximately a product state on A and C in terms of the trace distance, then what we can show is that it also satisfies this inequality, which, if you're familiar with this type of notation, directly implies the first one, but the other way around we would in general only have if sigma A and sigma C were lower bounded by some value. However, there is a way to get around this. It's somewhat technical though, so I'm not gonna go into too much detail here. And the second form of clustering that we can show and that we need is something that we call strong local indistinguishability, which is essentially a stronger form of what's in the literature known as local indistinguishability. And it tells us how the influence of faraway regions, how much of that decays in the distance of some small local region. Okay, so now we've seen decay of covariance implies decay of mutual information or max mutual information. And it turns out that, as I said before, decay of max mutual information also implies decay of mutual information, which implies decay of covariance. So we have for geometrically k-local commuting Hamiltonians this very nice equivalent of these three static properties. In fact, you could sandwich the decay of alpha Renyi mutual informations in here as well, and those also decay exponentially. And now you might be able to guess sort of what the next part is that I'm going to show, and that is that we're able to show that decay of max mutual information implies the existence of a suitably scaling MLSI constant. However, we can so far only show this for nearest neighbor interactions. So we need geometrically two local Hamiltonians. And with this, we have the main result of this work, and that is that gap, this property that I talked about in the beginning, directly implies rapid thermalization. And the nice thing is gap is a fairly well-studied property, which there is some literature about and we know quite a bit about. Whereas MLSI is more a new quantity that we don't know that much about. So having this implication sort of gives us a very, in some sense, weak condition for rapid thermalization. Now, this is sort of for the expert in the room. The main tools that we use to show this is we worked with, not with the Davies, conditional expectations, but with the mathematically a bit more tractable Schmidt conditional expectations. And then through this strong clustering result, we were able to show an approximate tensorization of the relative entropy with respect to these Schmidt conditional expectations, sort of leveraging that if the Gibbs state on two very far away regions is almost independent, then they should also thermalize almost independently from each other. And because the noise is local, sort of the global thermalization can then be split into many almost independent local thermalizations. And then if you put this back together, you get this global thermalization in with an MLSI that scales suitably. Okay. A bit more formal version of this gives us sort of a concrete scaling of an MLSI constant, namely that if we look at hypercubic lattices, then we can prove that there exists a constant, MLSI constant, meaning we get optimal rapid thermalization, and for trees, we get only a log decreasing one. Okay, now it turns out rapid thermalization also implies gap. So again, we have this very nice equivalent of these three dynamic properties: gap, rapid thermalization, and MLSI for nearest neighbor commuting Hamiltonians. Okay. Now let's compare this a bit to literature. If we consider systems with translational invariant Hamiltonians, then classically we know that on a one-dimensional lattice they thermalize optimally, so with a constant, LSI constant, which is the classical analog. Quantumly, we only knew that they had a log decreasing MLSI, and now we are able to improve this to a constant LSI. If we look at such systems on hypercubic lattices, then quantumly, there was actually no result for the Davies map, but for a different kind of thermalization, we had optimal thermalization. And now we can also show optimal thermalization with respect to the Davies here. And for trees, there we were not aware of any quantum thermalization results, and there we're able to show a log decreasing MLSI, hence also rapid thermalization, although not optimally. And if you care about this table in mixing times, this is the table in mixing times. So let me summarize. We've seen that for this very physically motivated type of thermalization, the Davies thermalization, we have that the gap is not just a necessary, but also a sufficient condition for rapid thermalization of nearest neighbor commuting Hamiltonians. And we also have this very nice equivalence of exponential decay of covariance, mutual information, max mutual information, and mixing condition. Okay, now what are some next steps? Well, one sort of obvious next step is, can we show this rapid thermalization also for more than nearest neighbor interactions? And there we have some ideas of how to do this. So let's see what happens in the coming months. The much more sort of interesting and complicated thing is, can we show this or similar results for non-commuting Hamiltonians? And non-commuting Hamiltonians do behave physically somewhat differently. So there we do expect different physics. So in this case, the question is, which are the requirements, sort of, or the additional constraints that we need to show rapid thermalization under gap? And this is this paper is one that's going to be presented tomorrow morning, if you're more interested in sort of non-commuting Gibbs state thermalization. And then the last thing is, so far we only considered quantum spin systems, meaning that on each part of the lattice we were considering some finite dimensional quantum system, some qubit. Now for bosonic systems, we also know that they physically behave differently, so there we also expect different physics if we consider bosonic degrees of freedom instead of finite degrees of freedom. And this is also a very interesting thing to look at. And with this, I want to thank you, and I'm happy to take any questions.
Great, thank you for the talk. So questions?
Yeah, thanks for a nice talk. I would like to ask that you said when it's a 1D, you can do K local in the table of the results. Yeah,
Yes,
after that, uh,
this one.
yeah. Here you say you can do K
Ah,
local.
yes. This the condition nearest neighbor interactions is only for more than 1D. So in 1D we don't have this requirement on nearest neighbor, and in 1D we also don't have the requirement on commutativity. The idea, or how you can see this, is you can always coarse grain your 1D spin chain such a way that it's nearest neighbor now, and this will still thermalize rapidly,
You said you don't need the commutativity.
at least for these results. Yes,
Then you have for 1D, you can do non-commuting.
we don't have this implication for non-commuting in 1D,
I see.
but at least this equivalence.
Oh, the equivalence of the correlation and
Yes,
decay
of these
of-
static things.
All
And
right.
there is, in fact, also a talk tomorrow about this equivalence for non-commuting by Angela, if you're interested in that.
Okay. All right.
Thank you.
More questions? I mean, I can ask one. So do you believe these results actually do hold for non-commuting and non-nearest neighbor? That you just can't prove them, or you think they might be false?
For non-nearest neighbor, I think they're true. And that's sort of just an artifact of using these Schmidt conditional expectations. For non-commuting, if the temperature is high enough, then they should also thermalize rapidly. But I'm not sure if we need an additional assumption to gap there.
And maybe as a follow-up to the nearest neighbor case, like when you say non-nearest neighbor, you mean like sort of k local but
Yeah.
k fixed. What if your interactions decay, say, exponentially or even as a power law?
I think if they decay exponentially, then we should also expect rapid thermalization. For power law or more long range, then I'm not sure.
Yeah. Oh, there's one there. So, and then sorry.
So what kind of condition imposed into your Lindblad operators, or so is that derived from the Davis so rotating wave approximations, or it can be any operator or any local operator?
Well, this sort of works not just for the Davies, but you need the dynamics need to be Markovian enough so that this works, and the Davies satisfy all of these things. Sort of the Schmidt dynamics that I briefly mentioned, they also satisfy these things. In some sense, you need what's called GNS symmetry, which is some sort of quantum detailed balanced condition, and you need frustration freeness.
Oh,
If you're
so you need a detailed balance condition for that.
Yes.
Oh, I understand. So can I ask another question? So yeah, I think if I understand correctly, Davis equation, the derivation for the Davis equation is only applicable to the small case. So if in the many body system it fails, I think so Bohr frequency becomes very small, and so the rotating wave approximation can be it's not valid for the many body system. So but you are considering many body system. So how do you think about that?
it's true, it's sort of arguable whether the Davies are the correct dynamics to look at, but the way I view this is the Davies are more physically correct than sort of local dephasing noise, or what's more often studied in literature. So maybe this is just one step towards a more complex type of thermalization. But as far as I'm aware, Davies is sort of a good paradigm, and I'm not aware of any well-established sort of dynamics beyond that. I mean, I think there's many sort of proposals, but none that really has is better than the others. This is actually quite interesting in the bosonic case, because there we need to consider different types of dissipation, and there it's not clear sort of what the correct one to look at is. Yeah, but that's a good point.
Okay, thank you very much.
Thanks for the talk. I just wanted to ask, how do you think the presence of symmetries, either globally or approximately held on some subsystem that you couple to the rest of the system for the bath, affects the discussion?
Do you have examples for?
Yeah. So I guess you have these bounds set by the spectral gap of the Limbladian, but
Mhm.
I guess it's not. It's a very general sense since you're like taking the minimum possible
Yeah.
choice there. But now if you have some prior knowledge of your system, like maybe there's a global symmetry constraint on both the bath and the system of interest, how does that affect maybe like the spectral properties and like therefore change the results on whether gap implies rapid thermalization, or if you're interested in the opposite, like sets bounds or limits on like quantum memories?
That's a good question. I think if the symmetries are large enough in some sense, then maybe they could prevent sort of rapid thermalization. But I'm not aware of rigorous results on this.
Mhm.
I mean, there are systems that we know that don't thermalize rapidly,
Mhm.
and usually those are very symmetric things, like the 4D toric code, for example. I don't know. That's a good question. I haven't really thought about that.
Okay, thank you.
Thank you.
Hi, do you know of any concrete examples where you say have a gap, but you don't have rapid mixing or you don't have LSI?
So we have a gap, but only
Yeah,
sort
so,
of polytime mixing and not
one where,
rapid mixing.
do you have a concrete example where one of these arrows definitely breaks down?
Not really,
Okay.
to be honest. This is why we think, but we're not quite sure, that all of these things should also hold in more general scenarios.
Okay. Thank you.
Any more questions? Okay, well, let's thank all speakers of the session.